A video on basically the most important concept in chemistry, the mole concept. The mole concept, go up a little here, is the most important concept in chemistry because it is a way of grouping small particles. This allows chemists to mass out, count, and find volume that's specific to a gas type of particle, of particles that are simply too small to be counted, massed, or find the volume for. So we have to group them together in large group settings. This is a concept that has gone back hundreds of years. The first two people who talked about it is a guy named Gay-Lussac, who came up with something called the law of combining volumes, which says that when two gases react together to form different products, the volumes of the reactants and products are in simple whole number ratios. Along with that, at about the same time, another person, I won't say his name because it's too long. His name is last name is Avogadro. What he was able to do was take the understanding that volumes of gases combine together in simple whole number ratios to form other simple whole number ratios products. He was actually able to relate it to the fact that those volumes contain particles, and those particles are actually made up of other particles that also combine in simple whole number ratios. This is about the time, maybe a couple, 50 to 100 years after Dalton came up with his concept of the atom. So this is kind of like an extension of that. And the reason why Avogadro gets the credit for this is because Gay-Lussac just kind of looked at the volume. Avogadro was able to take it and bring it down into the level of particles. And that's what we have today. So what we have done in the past, that was like 1800. So since that time, what we've come up with is we've been working on bettering the system, and we kind of flipped it from volumes to masses. In that time since then, we also learned a lot about different elements. And what we learned was the fact that we could figure out relative masses between elements, but not know the exact mass of any particular element. So that is one of the things we need. So back, a couple hundred years ago, a scientist could tell you that the mass of lead was this many times the mass of some other element, or some other element is only a partial amount, like 1/32 the mass of lead. So so that's important, but that doesn't give us what we need, because we're looking for actual masses. We've come a long way since then. We now know we know subatomic particles and the masses of subatomic particles. For example, we know the protons and neutrons weigh 1.67 times 10 to the 24, that's actually supposed to be 24th grams, and electrons are even smaller. But those numbers are incredibly small, and if you simply do a little exercise in looking at the largest atom there is, in assuming basically 300/1000 subatomic particles, with each subatomic particle weighing about 10 to the minus 24th grams, you would end up with the largest atom known weighing about 1 times 10 to the minus 21 grams. That's extremely small and something that we can't deal with. So therefore, we must create a grouping event so that we can. So, with that being said, relative mass between elements. We base our relative masses with a reference. The reference is carbon. Carbon weighs 12 grams. And at the time, they said it was AMUs, which is called atomic mass units. That's carbon. So what they found is that hydrogen is 1/12 the mass of a carbon. That's one hydrogen. Okay, so that'd be, sorry, that's not mass. That's just atoms. Okay? Which, put another way, if you have 1x of hydrogen, you have 12x of carbon. Which then you could also have 16 oxygen, which is 16 times massive than each hydrogen. And maybe you'll have sulfur that's two times the mass of an oxygen, which would be 32 times the mass of a carbon. And they were able to do this relative scale between all the elements. But again, all of those are just relative numbers. They're not actual numbers. So if we look at another way of doing it, is to explain it this way. That going this way, it's group size up top, and down here is increasing mass, increasing group size. So if I took one hydrogen atom and I assumed that it will weigh the maximum amount using subatomic particles of 100 protons to an electron, it's going to weigh approximately 1 times 10 to the minus 21 grams. Which, of course, a hydrogen atom doesn't weigh anything. That doesn't have that many subatomic particles. It basically has 1 or 2 or 3. But if we use the same discussion as here, that carbon is 12 times the mass of each hydrogen, then what we get is if one hydrogen atoms, one hydrogen atom weighs 1 times 10 to the minus 21 grams, then one oxygen atom must weigh, oxygen, therefore, it's oxygen, it's 16. Okay? Then one oxygen atom must weigh 16 times 10 to the minus 21 grams. Well, we can't weigh that. So we group them together. So let's say we group them into 1000s. So this is 1000 group. So if I have 1000 atoms of hydrogen, so 1000 atoms of hydrogen, it's going to weigh, if each of them weighs 1 times 10 to the minus 21 grams, it's going to weigh 1 times 10 to the minus 18 grams. So that's what 1,000 atoms of hydrogen. Therefore, 1,000 atoms of oxygen should weigh 16 times 10 to the minus 18 grams. I know I'm not using the correct scientific notation, but that's okay. So can I weigh these out? No, of course I can. So let's go to 1,000,000. So that's, again, I apologize. You're supposed to use scientific notation, but I'm just using it this way. So if I have 1,000,000, 1 times 10 to the 6th atoms of hydrogen, then if each hydrogen is 1 times 10 to the minus 21st, that mass of all of them must be 1 times 10 to the minus 15 grams. And again, if I have 1 times 10 to the 6 atoms of oxygen, it's going to be 16 times 10 to the minus 15 grams. Again, we can't weigh it. Now, this scale isn't the scale. So what we do is we keep on getting group sizes bigger and bigger and bigger until we can mass it out. In this case, hydrogen would be 1 gram of hydrogen, and therefore oxygen, okay, well, how big is this number size? 6.02 times 10 to the 23rd. That's the group size. So therefore, I would have 6.02 times 10 to the 23rd atoms of hydrogen in a way 1 gram. If I had 6.02 times 10 to the 23rd atoms of oxygen, it would weigh 16 grams of oxygen, because each oxygen atom is 16 times the mass of the hydrogen. So therefore, what it would look like is, it would look like 6.022 times 10 to the 23rd atoms of hydrogen would be equivalent to 1 gram of hydrogen. I don't use 6.02 times 10 to the 23rd. I use actually 6.02 times 10 to the 23rd. That number is what I use. Well, I'll put it over here in a second. So if I have 6.022 times 10 to the 23rd atoms of oxygen, it must weigh 16 grams of oxygen. And then I could do that for everybody else. Okay? So that's wonderful, and it worked extremely well, okay, except for the fact that the basis, when they did the basis, which is carbon, they didn't realize carbon had an isotope, and they had more than one isotope, so they had to correct it for isotopes. So these numbers here change ever so slightly, okay, and I'll get to that in a second. But people don't like to use the word, they don't like that number, 6.022 times 10 to the 23rd. So therefore, what we've done is we created a word. It's called the mole. And the mole, 1 mole, is equivalent to 6.02 times 10 to the 23rd. So if you have 6.02 times 10 to the 23rd atoms of hydrogen, you have 1 mole of hydrogen. If you have 6.02 times 10 to the, times 10 to the 23rd, sorry, if it's 6.02 times 10 to the 23rd atoms of oxygen, you have 1 mole of oxygen. Okay? So, again, what they found out once they got to the, when they found out what the fact that carbon was more than one thing, they had to pick one of the isotopes. So they picked carbon 12 isotope, and what it did is shifted these numbers around. And the actual numbers are 1.0078 grams of hydrogen and 15.99 grams of oxygen. And they should look familiar because this is the atomic mass. So what we have is this is an example, and I don't want to go to the example quite yet. So I'm going to add in, insert a slide right here. Okay. So what we have is a relationship. We have 1 mole of, let's say, hydrogen is equal to 6.02. I'm going to use 6.02 times 10 to the 23rd atoms of hydrogen. This is called Avogadro's number, in honor of Avogadro and what his starting assumption. Okay, what it does, it equals a certain mass. In this case, 1.0078 grams of hydrogen. And for example, oxygen, you can have 1 mole of oxygen, which is 6.02 times 10 to the 23rd atoms of oxygen, which is equal to 15.99 grams. So here is your massing relationship. So the first one is this to that, and I call it massing. So what happens is that it's a relationship, so it's a massing conversion factor. In essence, for every 1.0078 grams of hydrogen, you get 1 mole of hydrogen atoms. Now, the same thing for here, 15.99 grams of oxygen. You have you have 1 mole of oxygen. That's 1 mole oxygen atoms. Okay. Well, for first year kids, we don't get that specific. What we do is we round to a whole number. So you look on the periodic table, you look at atomic mass of atomic mass. So in this case, it would be 1 gram of hydrogen to for 1 mole of hydrogen atoms, and this is 16 grams. And 1 mole. Well, okay. The only exception is chlorine, and chlorine is 35.5 grams of chlorine in 1 mole. So you go to the periodic table, you look at atomic mass, the non-whole number thing, and you round to the whole number, and that's how many grams that element is. You weigh out to get 1 mole of that element, and you create these ratios. Okay, so that's what. If you go back down here, that's only one relationship. You have another relationship here, which is particles to moles. And then there's also a volume thing over here, which we'll get to later. Okay? So let me give you an example here. So down here, here's the equations. We get the equation is the number of moles is equal to the number of grams over atomic mass. And that is in grams per mole. Okay. Whoops. Okay. Counting is the number of moles is equal to the number of particles over 6.02 times 10 to the 23rd particles per mole. So the dimensional analysis, so that's equation. This is dimensional analysis. And dimensional analysis is exactly what you would assume to be. It's that relationship there. And over here, it's simply this. Put down there. And now leave volume to later. Okay. So an example of a very simple mass one is how many grams of carbon do I have? I have mass of 4.35 moles of C. So therefore, doing it out, I'm looking for grams of C. I know 4.35 moles of C, and I know the atomic mass, which is 12 grams of C in 1 mole of C. That's all above. I just don't have the space here. Okay. So this is also on a different sheet of paper. So doing it by dimensional analysis, what I'm going to have is I don't know if I'm going to put the grams, 12 grams of C over 1 mole of C or flipped upside down. That's determined by my first thing, which is there. But I know I want to get rid of moles on the bottom, get rid of it, so I'm going to use the 12 grams on the top, which is equal to that. Okay. By equation, we're going to take the number of moles is equal to the number of grams over the atomic mass, number of grams per mole. Okay, and I want the grams, so this is not the right equation. The right equation is number of grams. Sorry, I'll do that down here. The number of grams is equal to the number of moles times the number of grams per mole, which is exactly what that is. So if you do the math, it becomes 52.20 grams of C, which is equal to 52.2 grams of C. And so you could have done it down here as opposed to over there. Okay? So that's the basis of the first type, which is called massing, and these are elements. I hope that helps. More to come.